Bleeding means removing air from a hydraulic system. When pressure is applied to liquid in a hydraulic system, the liquid does not compress into a smaller volume. Pressure is transmitted without loss. Gases, however, are compressible. Pressure applied to air changes its volume, and some pressure is lost. That is why, if air enters a hydraulic braking system, it can be dangerous. Pressure on the brake pedal will not be transmitted in full through the system to apply the brakes. The brakes will be spongy. Bleeding the brakes means removing this air so that only liquid is left in the system. Friction is a force that resists the movement of one surface over another. It can be desirable, but often is not. It is caused by surface rough spots that lock together. These spots can be microscopically small, which is why even surfaces that seem to be smooth can experience friction. Friction can be reduced, but never eliminated. Friction is always measured for pairs of surfaces using what is called a coefficient of friction. A low coefficient of friction for a pair of surfaces means they can move easily over each other. A high coefficient of friction for a pair of surfaces means they cannot move easily over each other. Hydraulic pressure is transmitted through liquid. Since liquid is effectively incompressible, pressure applied to a liquid is transmitted without loss throughout the liquid. In a braking system, this allows a force applied to the brake pedal to act upon the brakes at the wheels. Hydraulic pressure transmits increased force. Since pressure is force per unit area, the same pressure applied over different areas can produce different forces, larger and smaller. This system has cylinders of different sizes. When the brake pedal is pressed, the force against the piston in the master cylinder applies pressure to the fluid. This same pressure is transmitted throughout the fluid, but it has a different effect on each piston in the other cylinders. The top cylinder is smaller than the master cylinder, so the force it exerts will be less than the force applied to the cylinder. The cylinder is the same size as the master cylinder, so the force from it will be the same too. The cylinder is larger than the master cylinder, and so is its force. A lever is basically a bar which is pivoted at some point called a fulcrum. An effort applied at some point on the lever overcomes a load at some point also on the lever. There are three basic types of lever: lever of the first order, lever of the second order, lever of the third order. They each have their own applications. The ratio of load and effort is called mechanical advantage. Using the right kind of lever in the right way allows a user to lift larger loads with smaller efforts. Most of a vehicle's weight is supported by its suspension system. It suspends the body and associated parts so that they are insulated from road shocks and vibrations that would otherwise be transmitted to the passengers and the vehicle itself. However, other parts of a vehicle are not supported by the suspension system, such as the wheels, tires, brakes, and steering and suspension parts not supported by springs. These parts are all called unsprung weight. Generally, unsprung weight should be kept as low as possible.
This section examines basic principles of the hydraulic braking system. Several factors can influence vehicle braking: road surface, road conditions, the weight of the vehicle, the load on the wheel during stopping, different maneuvers, and of course the tyres on the vehicle. An effective braking system takes all these factors into account. A basic hydraulic braking system has two main sections: the brake assemblies at the wheels and the hydraulic system that applies them. There is a brake for when the vehicle is in motion, usually a foot brake, and a park brake for when it's stationary, usually operated by hand. Some systems have all drum brakes. Some have disc brakes on the front wheels and drum brakes on the rear. Others have all disc brakes. A basic braking system has a brake pedal, a master cylinder to provide hydraulic pressure, brake lines and hoses to connect the master cylinder to the brake assemblies, fluid to transmit force from the master cylinder to the wheel cylinders of the brake assemblies, and the brake assemblies, drum or disc that stop the wheels. The driver pushes the brake pedal. It applies force to the piston in the master cylinder. The piston applies pressure to the fluid in the cylinder. The lines transfer the pressure to the wheel cylinders. And the wheel cylinders at the wheel assemblies apply the brakes. Force is transmitted through the fluid. For cylinders the same size, the force transmitted from one is the same value as the force applied to the other. By using cylinders of different sizes, forces can be increased or reduced. In an actual braking system, the master cylinder is smaller than the wheel cylinders, so the force at all of the wheel cylinders is increased. When brakes are applied to a moving vehicle, they absorb the vehicle's kinetic energy. Friction between the braking surfaces converts this energy into heat. In drum brakes, the wheel cylinders force brake linings against the inside of the brake drum. In disc brakes, pads are forced against a brake disc. In both systems, heat spreads into other parts and the atmosphere. So brake linings and drums, pads and discs must withstand high temperatures and high pressures. On modern vehicles, this basic system has some refinements, such as a power booster. This helps the driver apply the brakes. This section examines divided systems for disc brakes. Modern cars use tandem master cylinders to suit divided or dual-line braking systems. A divided system is safer in the event of partial failure. Fluid loss in one half of the system still leaves the other half able to halt the vehicle, although with an increase in stopping distance. A wheel's braking ability depends on the load it's carrying during braking, so the type of vehicle is a major factor in how its system should be divided. A front-engined rear-wheel drive car has around 40% of its load on its rear wheels, so its braking system can be divided in a vertical or front-rear split. This puts the front wheels in a different system from the rear wheels. If one half of the system fails, the front or the back, there's still enough separate braking capability left in the other half to stop the vehicle. This doesn't work well for a front-wheel drive vehicle. A load of about 20% on the rear wheels can't provide enough braking force to stop the vehicle. Front-engined, front-wheel drive vehicles use a braking system split in a diagonal or X. The left-hand front brake unit is connected to the right-hand rear unit, and the left-hand rear to the right-hand front. If one system fails, a 50% braking capability is left in the other system. Dual proportioning valves maintain optimum braking in each system. A system that partially failed would cause severe braking pull on a vehicle's suspension, so suspension geometry is usually revised to counter this. An alternative arrangement for front-engine rear-wheel drive vehicles is an L-split. The front disc brake units have 4 piston calipers. 2 of the pistons on each front unit connect to the right-hand rear, and the other 2 pistons of each unit connect to the left-hand rear. As with the X-split, if there is failure of either half of the system, it still leaves 50% braking capability. This section examines the disc braking system. Disc brakes can be used on all 4 wheels of a vehicle or combined with disc brakes on the front wheels and drum brakes on the rear. When the brake pedal is depressed, a push rod transfers the force through a brake booster to a hydraulic master cylinder. The master cylinder converts the force into hydraulic pressure, which is then transmitted via connecting pipes and hoses to 1 or more pistons at each brake caliper. The pistons operate on friction pads to provide a clamping force on a rotating flat disc that is attached to the wheel hub. This clamping tries to stop the rotation of the disc and the wheel. On non-driving wheels, the center of the brake disc or hub contains the wheel bearings. The hub can be part of the brake disc, or a separate assembly between the wheel and hub with nuts or bolts. On driving wheels, the disc is mounted onto the driving axle and may be held in place by the wheel. On front-wheel drive vehicles, it can be mounted on the front hub and wheel bearing assembly. The brake caliper assembly is bolted to the vehicle axle housing or suspension. In most cases, the brake is positioned as close as possible to the wheel. But there are exceptions. This high-performance car uses inboard disc brakes on its rear wheels. Its makers claim improved vehicle handling for this design because it reduces unsprung weight. Applying brakes can absorb a lot of vehicle energy, so friction between braking surfaces generates great heat. Brake parts withstand very high temperatures. Most of the friction area of a disc is exposed to air, so cooling is far more rapid than for a drum brake. Unlike drum brakes, brake fade is rare. Because of their shape, discs tend to throw off water. So after being driven through water, they operate almost immediately. Disc brakes need much higher pressures to operate than drum brakes. So almost all disc brake systems need a power brake booster to help reduce the pedal forces that are needed from the driver. Because of the high forces needed to apply a disc brake, using it as a handbrake is less common. Some vehicles build a drum brake into the center of the rear disc to provide for park brake operation. This section looks at the brake pedal. The brake pedal uses leverage to transfer the effort from the driver's foot to the master cylinder. Different lever designs can alter the effort the driver needs to make. It is usually suspended from a bracket between the dash panel and the firewall. In many vehicles, the brake pedal is either connected to a switch or in contact with one. It operates the stoplights when the brake pedal is depressed. This section looks at the master cylinder in disc brake systems. Most disc brake systems use a tandem master cylinder. It is connected to the brake pedal via a push rod. With a basic master cylinder in the braking system, Any loss of fluid, say because a component fails, could mean the whole braking system fails. To reduce this risk, modern vehicles must have at least two separate hydraulic systems. That's why the tandem master cylinder was introduced. Like two single piston cylinders end to end, a tandem cylinder has a primary piston and a secondary piston. Each section of the cylinder has an inlet and outlet port and a compensating port. There can be two separate reservoirs, or just one, but it is divided into separate sections. When the brake is applied, the primary piston moves and closes its compensating port. Fluid pressure rises and acts on the secondary piston. It moves, closing its compensating port. Pressure builds up in this circuit. Both pistons continue to move and displace fluid into their separate circuits and apply the brakes. If there is a failure in the secondary circuit, the primary system continues to operate normally, but with increased travel. If the primary circuit fails, no pressure is generated to move the secondary piston. So a rod attached to the front of the primary piston will push the secondary piston directly so that it still operates. A switch can warn of loss of pressure in the front or rear circuits. Or one that warns of low fluid level can be fitted to the reservoir. The tandem master cylinder can have problems with a low pressure area developing when the piston returns quickly, but the fluid lags. The tandem master cylinder overcomes this by using grooves in the side of the primary cup. These grooves allow fluid to flow from the inlet port into the low pressure area. This section examines brake lines. Brake lines carry brake fluid from the master cylinder to the brakes. They are basically the same on all brake systems. For most of their length, they are steel and attached to the body with clips or brackets to prevent damage from vibration. A flexible section must be included between the body and suspension to allow for steering and suspension movement. These flexible lines are made of reinforced tubing to protect them from objects that could be thrown by the tires. In some vehicles, the brake lines are inside the vehicle to protect them from corrosion. This section examines the proportioning valve. It divides up the braking effort applied to front and rear wheels under heavy braking, according to how load is distributed across a vehicle. The effectiveness of braking force is determined by tire-to-road friction, and this increases as load increases. Applying the brakes causes the front of this vehicle to dip. This causes greater tire-to-road friction on the front tires and less on the rear. This kind of change of load is called load transfer. So if equal braking force is applied to the front and rear wheels, the smaller rear load can make the rear wheels lock and perhaps skid. The braking force applied to the wheels needs to be adjusted to allow for changes in load. The proportioning valve adjusts braking force to allow for load transfer. It can be pressure sensitive or load sensitive. The pressure sensitive valve can be in the master cylinder or in a separate unit in the rear brake circuit. The load sensitive type can be in the body or the axle, where it can respond to load changes and change the braking effort as needed. Master cylinder applications usually combine the proportioning valve with a pressure differential switch. In normal braking, the poppet piston is held in a relaxed position by a large pressure spring. The poppet valve is held against its retainer by a light return spring, and fluid passes freely through the valve to the rear brakes. In heavy braking, master cylinder pressure can reach a valve's crack point. The pressure applied to the two different areas of the poppet piston creates unequal forces. That moves the poppet piston against the large pressure spring. This action holds the conical section of the valve against the seat, which limits the pressure increase to the rear brakes. As greater pedal force increases pressure in the master cylinder, fluid pressure rises on the smaller end of the piston. This combines with the force of the pressure spring to overcome the lower pressure now on the larger end. This forces the piston back, clear of the poppet valve. The increased pressure now acts on the larger end of the poppet piston and again forces the piston forward to contact the valve. When the pedal is released, the pressure of the rear brake fluid unseats the poppet valve, letting fluid return to the master cylinder. The pressure spring now returns the poppet piston to its relaxed position. Should the front brake system fail, the warning lamp spool moves forward, taking the poppet valve with it. Pressure in the rear brakes rises and the piston moves forward, but it can't seal on the valve. Should the rear brake system fail, the warning lamp spool will move backwards to activate the warning light. The proportioning valve doesn't operate in this situation. On a diagonally divided system, the pressure-sensitive proportioning valve is usually located away from the master cylinder. There is one for each circuit. They each operate in a similar way to the pressure-sensitive proportioning valve located in the master cylinder, but without the pressure differential warning light circuit. The load-sensing proportioning valve is usually located in the rear brake circuit on the chassis. A diagonally split system may have two load-sensing proportioning valves, one for each brake. The unit is mounted on the chassis around the rear suspension. This section examines the power booster. A power booster or power brake unit uses a vacuum to multiply the driver's pedal effort and apply that to the master cylinder. This increases the pressures available from the master cylinder. Units on petrol engines use the vacuum produced in the intake manifold. Vehicles with diesel engines cannot use manifold vacuum, so they are fitted with an engine-driven vacuum pump. The most common booster now operates between the brake and master cylinder. It increases the force that acts on the master cylinder. Whenever the pedal is depressed, the power brake unit assists the driver. The level of assistance depends on the pressure applied. When the driver moves the brake pedal pushrod, it transmits movement through the power unit to the master cylinder piston to apply the brakes. It also operates a control valve that admits air at atmospheric pressure to the rear of the unit. How it works depends on the position of the pushrod. A hose connects the intake manifold to a vacuum check valve on the power unit. With the engine running, the vacuum in the intake manifold is used to evacuate the power unit. This valve is held off its seat and a vacuum is produced in both chambers of the unit. The chambers are separated by a flexible rubber diaphragm attached to the diaphragm plate. It is held in the off position by a diaphragm return spring. The master cylinder pushrod and the control valve assembly are centrally located on each side of the plate. As the brakes are applied, the pedal pushrod and plunger move forward in the diaphragm plate. This brings the control valve into contact with the vacuum port seat. It closes the vacuum port. sealing off the passage connecting the chambers. Further movement of the push rod and plunger moves the air valve away from the control valve to open the atmospheric port. Air at atmospheric pressure comes into the air filter and passages and enters the chamber at the rear of the diaphragm. The difference in pressure now on both sides of the diaphragm moves the diaphragm plate forward, and it takes the master cylinder push rod with it. Hydraulic pressure builds up in the brake system to operate the brakes. As pressure rises, a counterforce acts through the master cylinder push rod and the reaction disc. This counterforce acts against the plunger and pedal push rod. It tends to move the plunger slightly to the rear, and it closes off the atmospheric port. If the vacuum source is interrupted, then as the pedal is pushed down, the pedal push rod and plunger assembly come in contact with the reaction disc. This forces the master cylinder push rod forward to operate the brakes. The pedal force needed then is much greater than with vacuum assistance. During application, the reaction force against the valve plunger works against the driver to close the atmospheric port. With both the atmospheric and the vacuum ports closed, the power unit is in a holding position. It stays this way until increased pedal force reopens the atmospheric port, or a drop in pedal force reopens the vacuum port. With the force on the pedal held constant, the valve returns to the holding position. But if the pedal is fully applied, the plunger moves away from the control valve to open the atmospheric port and give full power application. When the brakes are released, vacuum returns to both sides of the diaphragm, so the spring releases the brakes. When the engine is switched off or stops for any reason, no vacuum is available. The vacuum remaining in the booster, held by the non-return valve, will provide for at least one power-boosted application. After this, the brakes will still operate, but without power assistance, they require more effort from the driver. This section looks at the emergency brake for the disc brake system. All vehicles must be fitted with at least two independent systems. They were once called the service brake and emergency brake. Now they are usually referred to as the foot brake and the park brake. Most light vehicles use a foot brake that operates through a hydraulic system on all wheels, and a hand-operated brake that acts mechanically on the rear wheels only. One common use of the handbrake system is to hold the vehicle when it is parked. The systems are designed to be independent so that if one fails, the other is still available. This light commercial vehicle uses a single drum brake on the rear of the gearbox as a handbrake. It's sometimes called a transmission brake. Some incorporate a drum brake for the handbrake in the center of the rear disc brake. Others use a mechanical linkage to operate the disc brake from the handbrake system, or separate handbrake calipers with their own pads. Some vehicles have the handbrake operating on the front wheels. This section examines brake fluid. The brake fluid transmits hydraulic pressure from the master cylinder to the wheels. It is a special fluid with special properties. Most are a mixture of glycerin and alcohol, called glycol, with additives to give it the characteristics that are needed. It must have the correct viscosity for hot and cold conditions. Its boiling point must be higher than the temperature reached by the system. It must not damage seals, gaskets or hoses or cause corrosion. Glycol-based fluids meet most requirements, although they do damage paint. And they absorb moisture, hence the warnings. This is important because as moisture is absorbed, it lowers the boiling point of the fluid. Brake fluid should not be mixed with mineral-based oils or solvents. If contamination is suspected, the braking system must be drained and flushed with a suitable solvent and rubber components replaced. This section looks at the brake disc or rotor. The brake disc or rotor is the main rotating component of the disc brake unit. It's usually made of cast iron because it's hard-wearing and can resist high temperatures. On motorcycles, it is often made of stainless steel. Most brake discs are stamped with the manufacturer's minimum thickness specification. When the pad wears, if the thickness of the disc were below this minimum, the piston may go beyond the sealing edge. Ventilated discs can be used to improve cooling. These slots are designed to use centrifugal force to cause airflow when the disc is rotating. Some discs are drilled or slotted on their friction surface to improve cooling and assist with removing water. This section examines disc brake pads. Disc brake pads consist of friction material bonded onto a steel backing plate. The backing plate has lugs that locate the pad in the correct position in relation to the disc. Calipers are usually designed so that the condition of the pads can be checked easily once the wheel has been removed, and to allow the pads to be replaced with a minimum of disassembly. Some pads have a groove cut into the friction surface. The depth of this groove is set so that when it can no longer be seen, the pad should be replaced. Some pads have a wire in the friction material at the minimum wear thickness. When the pad wears to this minimum thickness, the wire touches the disc as the brakes are applied. A warning light then tells the driver the disc pads are due for replacement. The composition of the friction material affects brake operation. Materials which provide good braking with low pedal pressures tend to lose efficiency when they get hot. This means the stopping distance will be increased. Materials which maintain a stable friction coefficient over a wide temperature range generally require higher pedal pressures to provide efficient braking. This section examines disc brake calipers. The disc brake caliper assembly is bolted to the vehicle axle housing or suspension. There are two main types: fixed and sliding. Fixed calipers can have 2, 3, or 4 pistons. Two-piston calipers have one piston on each side of the disc. Each piston has its own disc pad. When the brakes are applied, hydraulic pressure forces both pistons inwards, causing the pads to come in contact with the rotating disc. The sliding or floating caliper has 2 pads but only one piston. The caliper is mounted on pins or bushers that let it move from side to side. When the brakes are applied, hydraulic pressure forces the piston inwards. This pushes the pad against the disc. The caliper is free to move on slides, so there is a clamping effect between the inner and outer pads. Equal force is then applied to both pads, which clamp against the disc. In disc brake calipers, the piston moves against a stationary square section sealing ring. When the brakes are applied, the piston slightly deforms the seal. When the brakes are released, the seal returns to its original shape. The action of this sealing ring retracts the piston to provide a small running clearance between the disc and pads. It also makes the brake self-adjusting.